Hi there everyone and welcome to Cambridge Advanced Level Mathematics. My name is Ferguson Mangoma, and in this video we want to discuss integrals of the form 1 over a cosine of theta plus b sine of theta. Now the method that we are going to discuss here is called the t-substitution method. It's the t-substitution method. Now, so let's develop the method step by step. The first thing that we want to imagine is that we have a right-angled triangle like this. There is our right-angled triangle there. Let it be right-angled. Let's label it A, B, C. And let this triangle be right-angled at B. Let the angle at A be equal to theta over 2. Let the length of side BC be equal to T. Let the length of the side AB be equal to 1. Now, once we have done this, certain things follow directly from this. The first thing, of course, is that the tangent of theta over 2, which we know is BC opposite over adjacent, will be equal to T over 1, which is just equal to T. So straight away, tan of theta over 2 is equal to T. Let me write it here. Tan of theta over 2 is equal to T. Okay, because I want to write something here. Now, from Pythagoras' theorem, we also know that this is the hypotenuse, and the length of the hypotenuse squared is equal to this side squared plus that side squared. So therefore, the length of the hypotenuse is equal to the square root of this plus this squared plus that squared. So we can write here, this is of length t squared plus 1 square root of all that. That's just from Pythagoras' theorem. Okay, now we have got the length of all the sides, and we've got our nice angle there, theta over 2. What about the other trigonometrical ratios? Our sine of theta over 2 and our cosine of theta over 2. Well, sine of theta over 2 is equal to, I hope I don't block, let me come over here. Sine of theta over 2 will be given by sine of theta over 2 is equal to this side over that side, which is equal to T divided by the square root of T squared plus 1. What about cosine of theta over 2? It is equal to adjacent over hypotenuse, which is equal to cosine of theta over 2 is equal to 1 over T squared plus 1. Now we've got all our trigonometrical ratios, sine of theta over 2, cosine of theta over 2, tan of theta over 2. We are now all of them expressed in terms of T. But when we look at our integral here, because remember our destination is to replace everything that is expressed in terms of theta and start expressing it in terms of T. And the theta also, we have to change the variable of integration there. So when we look at our integral here, this is cosine of theta and this is sine of theta. It's not sine of theta over 2. It's not cosine of theta over 2. It's not tan of theta over 2. So we need to change this cosine of theta and express it in terms of cosine of theta over 2. Change this sine of theta and express it in terms of theta over 2. How can we do that? Double angle formulas. We know that sine of theta, when we use double angle formula, is equal to 2 multiplied by sine of theta over 2 cosine of theta over 2. But we now know what sine of theta over 2 is, and we know what cosine of theta over 2 is. So we can say this is equal to 2 brackets t over root of t squared plus 1 bracket multiplied by cosine of theta over 2, which is equal to that, which is 1 over t squared plus 1. We close our bracket. This we can simplify to this multiplies itself and the square root sign disappears. And on top we've got a 2t. So this becomes a 2t over 1 plus t squared. It becomes 1 plus t squared because this squared, this and that squaring, the square root sign disappears. So this is our sine of theta. What about cosine of theta? Cosine of theta is equal to, when we use the double angle formula, cosine of theta is equal to cosine squared theta over 2 minus sine squared theta over 2. Well, we know the expression for cosine of theta over 2 and that for sine of theta over 2. So we can replace that and say this is equal to 1 over the root of t squared plus 1 all squared, because look, it's squared, minus that one there squared as well, t over the root of t squared plus 1 all squared. When this one squared, the square root sign disappears. When we square that, the square root sign disappears. So we are left with 1 over t squared plus 1 minus the here, it's a t squared, so it becomes t squared over 1 plus t squared. This simplifies because there's a common denominator. This simplifies to 1 minus t squared over t squared plus 1. This is what cosine of theta is. Okay, so we've got this and we've got that. Remember, we're doing all these things so that we can replace this with something in terms of t. We can replace that with something in terms of t. So we're done with this, we're done with that. What is left now is to find an expression for d theta in terms of dt. Okay, now we do have this as well. So it's 1 here, 2 here, and 3 here. These are the expressions that we want. Now, what can I do? I'm trying to think of what I can get rid of because I want to book this thing somewhere and leave one of the boards free. Okay, so I'm going to clean this side. So I'll put these ones here. We're done with that one. Right, so our cosine of theta now, we have found it's that. So it's equal to 1 minus t squared over 1 t squared plus 1. And our sine of theta, which is that one there, is equal to 2t over 1 plus t squared. And of course, our tan of theta over 2 is that. So we need all this. Let me just put this one here. So tan of theta over 2 is equal to t. We don't need to change this one to tan of theta. I will show you why. So let's first of all clear some space here so we can complete our development of the t-substitution formula. Okay, so now remember we said we've done this, we've done that, what we're left with is that. How do we do that? Let's use this expression here. It says t is equal to tan of theta over 2. Let's differentiate both sides with respect to theta. We will get dt over d theta is equal to half sec squared theta over 2. Remember, the derivative of tan of theta is sec squared theta. So this is tan of theta over 2, so it becomes half sec squared theta over 2. Well, we also know that there is an identity that links sec squared theta plus tan squared theta. This is equal to 1 plus 6 tan squared theta over 2. So we can write this as 1/2 multiplied by 1 plus tan of tan squared theta over 2. Remember, sec squared theta is equal to 1 plus tan squared theta. So I've replaced sec squared half theta here with 1 plus tan of half theta squared. So, but we know that tan of theta is equal to t. So I can write this as half of 1 plus t squared. Remember, this is equal to that. So dt d theta is equal to that. Let's multiply both sides by 2. We get 2 dt d theta is equal to 1 plus t squared. Let's take the theta over to that side. Then we are left with, this means 2 dt is equal to 1 plus t squared multiplied by d theta. You know where we are going, don't you? We divide both sides by 1 plus t squared. We now have 2 dt over 1 plus t squared is equal to d theta. So now we can replace this with that, replace this with that, replace this with that, and we complete our change of variable. Now let's see, let me book this somewhere down here. Okay, let me just write it somewhere here. So let's do that. I'll write it here. It's d theta is equal to 2 dt over 1 plus t squared. Okay, right. Let's clear some space so that we can complete our substitution there. So what we have now is the integral with respect to theta of a cosine of theta plus b sine of theta becomes the integral. Our d theta now is replaced by that. So we have 2 dt over 1 plus t squared divided by all this. We have a multiplying cosine of theta. My cosine of theta is that, which is 1 minus t squared over 1 plus t squared, brackets, plus b multiplying my sine of theta, which is equal to 2t over 1 plus t squared, close bracket. All right, this is under the same denominator, so we can simplify this to the integral of 2 dt over 1 plus t squared, all divided by 1 plus t squared over this one here, it's 1 minus t squared plus 2t. Okay, we can flip this thing upside down and then it becomes the integral of 2 dt over 1 plus t squared multiplied by now multiplied by, this one comes on top and it becomes 1 plus t squared divided by 1 minus t squared plus 2t. This cancels and that cancels. And what is left now is 2 dt over 1 minus t squared plus 2t. Now, what we have done is we replaced all the thetas with something in terms of t, and our d theta was replaced by dt. That completes our change of variable. That's why it's called the t-substitution. So what is left now is to integrate. One can complete this square and end up with something perhaps in the form of ln t or something. But when you have completed the integration, you have to revert back to your theta, remembering that your t is equal to tan of theta. So whatever you get here in terms of theta, remember to go back and replace your t with tan of theta, and the integration is completed. What I'm going to do is, in my next video, I am going to come up with a specific example using the method of the t-substitution. You can go and try to integrate this. It's a pretty simple. My advice is try to complete this square, and then from there you get a nice expression which is integral. Till see you again. Bye-bye and thank you.